Here we go. Accelerated Chemistry Practice Test. Your problems on the test, like I said, we're getting to the point where we've covered so much information, we can express it in one problem. Of course, that problem requires many steps, and you've got to think your way through this, which is why I really like molarity, thermochemistry, stoichiometry. We'll see this again with gas laws. Also, again, we've got a whole huge, broad base of information now, and making all of that work in a problem is where it really gets interesting. So, number one, what would the final temperature of 500 milliliters of a 2 molar hydrochloric acid solution be if the water had an initial temperature of 21 degrees Celsius? The molar heat of solution for hydrogen chloride is negative 74.84 kilojoules per mole. We're assuming that the 500 milliliters of water are used to make the solution. Really, when we're talking about molarity, it's moles of solute per liter of solution. So when we add the hydrogen chloride to the water to make hydrochloric acid, we'll actually have slightly more than 500 milliliters of solution. But for our purposes here, we're doing enough. We don't have to worry about the amount of water that's displaced by the hydrogen chloride, because maybe it would be 490 milliliters of water that we'd actually use to make this solution, fairly close to 500. I just want to make sure we can do the process for this particular reaction. So, this combines molarity, this combines thermochemistry, and if you remember, thermochemistry is basically just stoichiometry with energy factored in. So my first thing, you got to think your way through. I have a amount of heat released per mole for hydrogen chloride. So I'm going to get energy there. I mentioned specific heat, but in either way, we see that water is going to heat up. That's a specific heat problem. So I have a thermochemistry problem, I have a specific heat problem, and I also have a molarity problem. I have here units per mole. And remember, the negative number here means that heat is released. So really the first thing that's happening, I have hydrogen chloride, which is a gas, and I turn that into hydrogen ions dissolved in solution and chloride ions dissolved in solution. Hydrogen chloride dissociates in water. It forms an acid. Anytime you have H+ floating around, that's an acid. Now this is an exothermic reaction because of the negative number. We're still dealing with positive energy. None of this is negative energy. That's for physics. That's for very complex physics. But this is energy that's coming out of my reaction. So it's energy that's coming out of hydrogen chloride, released into the system, just like the hydrogen ions and the chloride ions. So that's 74.84 kilojoules for 1 mole. For 1 mole of hydrogen chloride, I got 1 mole of hydrogen ions. That'll be important very soon when we talk about acids and bases. I get 1 mole of chloride ions, and I get 74.84 kilojoules of energy. That is very important to know. From there, this is a molar heat of solution. I want to find out how many moles of hydrogen chloride went into that solution. I can do that by having my 2.0 moles per liter equals my moles of solute over 0.5 liters of solution. I have to change, since molarity is moles per liter, I have to make sure I change my milliliters into liters, which shouldn't be all that complicated. I multiply both sides by 0.5, I end up getting 1 mole of hydrogen chloride. So I cut you a break there, and I made it 1 mole of hydrogen chloride. 1 mole of hydrogen chloride, if I wanted to really be thorough about this, I want to find out how much energy is released by 1 mole of hydrogen chloride. Well, my molar heat of solution is 74.84 kilojoules for 1 mole of HCl. This cancels out. and I end up with 74.84 kilojoules. That is the energy that was released when 1 mole of hydrogen chloride is dissolved in water. Now, from there, that mole was dissolved in water. That energy was released into the water. So we have a nice little equation to deal with energy being put into any substance. In this particular case, we're talking about water. And I gave you the specific heat of water. But notice the units. We're talking about joules here. This is in kilojoules. We must change our kilojoules into joules. Now, again, if you want to be very thorough about this, we did a lot of unit conversions at the beginning of the year. 1,000 joules over 1 kilojoule. My kilojoules cancel out. I end up with 74,840 joules. That is the amount of energy that goes into my water. So, 74,840 joules equals the mass of my water. Now in this case, again, water is nice because 1 gram of water, it fills the volume of 1 milliliter. That's one of the standards for a gram. 1 cubic centimeter or 1 milliliter of water weighs 1 gram. So 500 milliliters of water weigh 500 grams. Again, keeping my units consistent. I'm talking about grams there. So 500 grams, specific heat, 4.18. Of course, if this were calories, we'd have to convert calories, joules to calories or kilojoules to calories. We don't have to worry about that. I just want to make sure you see what this process is. And this is change in temperature. We'll make sure we remember that very soon. But first off, I'm going to do my 500 times 500 times 500 times 4.18 equals 2090. Okay, so divide this side by 2090, divide this side by 2090. Now, if I really was careful about my units and everything, I noticed that all of my units will cancel out. All I'll be left with is degrees Celsius. But I think we've moved beyond that point of having to worry about that. It might actually be more complicated if we worry about canceling out all the units. Just know you had to plug in the numbers where they need to go. Unfortunately, much of the rest of this year is just going to be plugging in numbers. So this is kind of getting us along that path. But you still have to think your way through a problem. So 74,840 divided by 2090 is 35.8. So 35.8 equals delta T. This is why we need to be very careful when we're dissolving our... Let me make sure I'm recording here. Yes, okay. This is why we have to be very careful when we're dissolving our acids in water. That temperature went up very substantially. That's 35.8 degrees Celsius. I started at 21 degrees Celsius. This is my change in temperature. Since this is an exothermic reaction, the heat is released into the system, which means the temperature goes up. So if I have my initial temperature, and with the sig figs we only have 2 of them, so here we'd only use 2 also. 21 plus 36 degrees Celsius, that water temperature went up. And this is not a very highly concentrated hydrochloric acid solution. 1 molar is not very, very concentrated. 12 molar is what you can get up to with hydrochloric acid. That's where we're talking about a tremendous amount of heat. We're talking about more than 10 times this amount, which means you're going to be boiling, probably going to be boiling the water, or at least making it scalding hot as you're mixing your acid. This is why we need to be very careful being aware of molar heat of solution. So 7 and 5, we raise the temperature of that water to 57 degrees Celsius. And that is what I'm asking for, because it says, what would the final temperature be? Make sure everything you do works towards that goal. I found out how many moles that I had. I found of hydrogen chloride. I found out how much energy that was. I fed that energy into specific heat, and I solved for change in temperature. This is going to be very important for everything going forward, is taking what you know and finding the path to get you to where you need to be. Let me readjust now so we can go to the next problem. Again, I apologize for the low tech here, but my computer doesn't have all the fancy bells and whistles, and that would take actually a lot more time. I'm trying to get this out as quickly as I can, hence the very low tech process here. All right, so second question. How many grams of lead-2 iodide should precipitate? We're talking about a double replacement reaction. If 358 milliliters of 0.2 molar lead nitrate is mixed with 450 milliliters of 0.25 molar sodium iodide. So this is a good old double replacement reaction. If you checked your solubility rules, which we have on the back of this sheet, I would know that iodides are soluble except for lead-2 is not soluble. My nitrates, all of them are soluble. So just to review very quickly here, I have lead nitrate, lead-2 nitrate. Nitrate has a -1 charge. So I need 2 nitrates to balance my lead-2. I have sodium iodide. And again, all of the alkali salts are soluble in water. And this will give me lead-2 iodide, which is a precipitate, and sodium nitrate, which remains aqueous because all nitrates are soluble, no exceptions. Now this is not balanced. My first step in any stoichiometry problem is to balance my equation. Now if I look, I have 2 nitrates here. If I put a 2 here, I get 2 nitrates. 2 iodides. If I put a 2 here, 2 sodiums, 2 iodides, I'm now balanced. 1 lead, 2 iodides, 2 iodides, 2 nitrates, 2 nitrates, 2 sodiums, 2 sodiums. I am perfectly balanced now. If I were really asking for everything, I might do a net ionic equation here. Lead-2 is going to be floating around in solution. 2 nitrates are going to be floating around in solution. Sodium is going to be floating around in solution. Iodide is going to be floating around in solution. The fact that sodium and nitrate are floating around has no bearing on this actual reaction. If I wanted to do a net ionic equation, just so we don't forget, that's what's important. 2 iodides and 2 leads. They come together and they form lead-2 iodide. That would be a net ionic equation. Make sure you remember that. You might see that like on a final exam. Be aware of it. Okay, so I have my balanced equation. That's the first step in any stoichiometry problem. Now I'm given amounts of 2 of my reactants. So my next step is a limiting reactant problem. Which one of these is going to run out first? How am I going to do that? I have lead nitrate. I'm sorry, that should be lead-2 nitrate. How dare I make a typo? Okay, 0.2 molar would be X moles over 0.358 liters. I have to have it in liters because molarity is moles per liter. So for 1 liter, I would have 0.2 moles. For 0.358 liters, I have 0.0716 moles of lead-2 nitrate. Now, that's how many moles of lead 2 nitrate. How many moles of sodium iodide? In 1 mole, I would have in 1 mole I have 0.25. In 1 liter, I would have 0.25 moles in 1 liter of solution. I don't have 1 liter, I have 0.450 liters. So, again, 0.25 times 0.450 equals 0.1125 moles of sodium iodide. With the limiting reactant problem, my next step is to find out how much product. Which product would I focus on? Well, it's asking for lead 2 iodide. Whichever one of these runs out first stops the reaction. Therefore, whichever one of these is going to give me the least amount of product, that is my limiting reactant. So, 0.0716, it's going to ask for grams, but I'm going to feed these through my mole ratio. Again, stoichiometry, balanced equation, units to moles. A little bit more complicated way of going from units to moles, but same exact idea. From there, my mole ratio. Can you cross multiply? Absolutely. So I'd have 1 mole of lead nitrate over 1 mole of lead iodide equals 0.0716 moles of lead iodide over X, and I'd solve for X. However, the faster way to do that is this: 1 mole of lead 2 iodide. Oh, that's very sloppy. 1 mole of lead 2 iodide over 1 mole of lead 2 nitrate. I got that from my equation. And that means that I would make, in this particular case, if all of my lead 2 nitrate runs out, my units here cancel out, I would end up making 0.0716 moles of lead 2 iodide. I got a little bit cut off, but lead 2 iodide. I realized my camera's not exactly where I need it to be. So 0.0716 moles of lead 2 iodide. Now, the other one, so if all of my lead 2 nitrate gets used up, I make that much lead 2 iodide. In this case, what's the ratio that I'm going to feed this through? I want to cancel out sodium iodide. 2 moles of sodium iodide. What do I want on the top? 1 mole of lead 2 iodide. How am I looking at that? For every 2 moles of this sodium iodide, I make 1 mole of lead 2 iodide. If I had 1 mole of sodium iodide, I would make a half a mole of lead 2 iodide. So really, for any amount of sodium iodide I have, I get half the amount of lead 2 iodide. And look at this. The way I set this up, I'm dividing it by half. So this would be 2 times 1 over 2. That would give me 1. This is what I want to keep doing. So in this case, 0.1125 divided by 2, as my equation is set up, I would produce 0.05625 moles of lead 2 iodide. Which one produces less lead 2 iodide? This one. Which one is my limiting reactant? It is sodium iodide in this particular case. From there, I want to find what my actual yield is. How would I find the actual yield? Well, first I need to find theoretical yield. Percent yield is actual over theoretical times 100. In this case, I know my percent yield. In this case, I don't know what my actual is. I can find my theoretical. How do I find my theoretical yield? 0.05625 moles of lead to iodide. Multiply that by my gram molar mass. Now this is a pretty monstrous formula unit because I'm dealing with some very large atoms. So lead is 207.2, and then iodine is 126.9. So 207.2 plus 2 times 126.9 equals 461 grams per mole. Just to double check my work to make sure I'm not giving you any incorrect answers. 126.9 times 2 equals 253.8 plus 207.2 is 461. Okay, we're good. Either way. Now, 461 times 0.052, 461 times 0.05625 equals 25.9 grams of lead to iodide should have been produced. Should have been produced. That is my theoretical yield mathematically based on what I got in the top part. The actual yield is 78% of that. So 25.9 times 0.78 equals 20.2 grams. I'm dealing with, really truly I'm dealing with two significant digits. So 20 grams, 20 grams of lead to iodide would be the most appropriate answer. The actual yield is 20 grams of lead to iodide. Again, this is looking at the situation slightly different. I don't want to just make you computers that has to just give you a number and feed it through. I want you thinking about what's going on here, because this is going to be, for any higher order science class, you're going to have to think your way through problems.